Now that we have an idea of how to graph polynomials based upon their roots, we're going to step it up a little bit in complexity and deal with what we call multiplicity in roots and how that affects the graph of a polynomial. So we're going to look at some examples of some power functions and some power functions with horizontal translations to sort of get some intuition about how this might work. We're going to study the example of a polynomial with more than one repeated root. And then we're going to apply these principles to a slightly more complex example. All right, let's take a look. So we're just going to look at power functions right now. We'll look at x to the 1. That is not a very exciting power function. That is just a line. And notice that it cuts right through the x-axis in a straight line going down to up. It's increasing, right? So for x squared, it's a little bit different. That one is a nice parabola. It sits right there on the x-axis at x equals 0. If we look at x cubed, that one starts from the left, goes uphill, cuts through the x-axis, and keeps on going. X to the 4th looks not exactly the same as x squared. It's actually technically not a parabola, but it looks very parabola-like. And it sort of sits on the x-axis at x equals 0, just like x squared did. If we look at, and so our patterns are that it looks like in all these cases, all functions have a single intercept at x equals 0. If we have an odd power of x, that's going to cut through the x-axis at the x-intercept. And if we have even powers, that's just going to skim the x-axis at the x-intercept and then go in the opposite direction. So it's going to go down and then up. But you can imagine that if we had a negative coefficient, it could skim the x-axis going up and then down. So what if the x-intercept is not at x equals 0? Is this going to affect our rule about the exponents at all? So let's look at what happens when we have x minus 3 squared. What's that going to look like? Well, it looks just like x squared. We just sort of translated it to the right. X minus 6 cubed? Yeah, same thing. We just translated that to the right 6 units as well. So changing the roots doesn't change the rule of odd versus even. All it does is it shifts the graph horizontally so that it hits the x-axis at a different place. So same rules apply. Now things get one more level of complicated. We're going to see what happens if we have more than one x-intercept for our polynomial. So let's say we have something like x minus 2 cubed times x minus 5 to the 4th. Let's see what Desmos tells us about that graph. That one's kind of funky. Look at that. Well, I mean, there are certain things that we'd expect. We expect it to have an x-intercept at x equals 2, right? That's what makes x minus 2 cubed equal 0. We expect it to have an x-intercept at x equals 5. That would make x minus 5 to the 4th equal 0. Notice what happens at those two x-intercepts. They behave a little bit differently, right? At x equals 2, looks exactly like the graph x minus 2 cubed. It sort of cuts through the graph just like x minus 2 cubed would. And if we look at x equals 5, that looks a lot like what x minus 5 to the 4th is going to look like. It just skims the graph. So it appears these odd-even rules apply even when we have more than one x-intercept. So here's the summary. If you have a root at x equals, x equals a, then x minus a is going to be a factor of f of x. That's not surprising because if you take x minus a and plug in x equals a, that makes x minus a equal to 0. That makes the whole thing equal to 0. So yeah, x minus a being a factor of x, not a surprise. Now we might have a higher power of x minus a. It just might just be x minus a that's a factor. We might have x minus a squared, x minus a cubed, x minus a to the 4th. And depending on what that exponent of x minus a is, if it's odd, then the graph is going to cut through the x-axis, just like x minus a, just like x minus a cubed, just like x minus a to the 5th. And if that same exponent k is even, then the graph is going to skim the graph, much like x minus a squared, x minus a to the 4th, etc. So as long as we understand these principles and the way we understand our end behavior, which we're actually pretty good at that by now, that enables us to sketch graphs. All right, so let's look at this one. This one looks like a mess, right? This is 3 times x minus 1 squared times x minus 2 cubed times x minus 3 to the 4th. And we're trying to figure out what that graph is going to look like just based upon its roots, just based upon those exponents, and based upon what we can figure out about its end behavior. So let's do the end behavior first, because actually that one looks like it's going to be pretty awful, but it's really not. So first of all, let's think about what that highest exponent is going to be. Now, you're going to get powers of x from that x minus 1 squared. How many factors of x can you possibly get maximum from that x minus 1 squared? Well, if you square that out, you're going to get 2, right? You'll get x squared from squaring out x minus 1 squared. What about the x minus 2 cubed? You'll get 3 more factors of x, right? If you were to cube that one out, you're going to get x cubed as your highest one. When you multiply that by x squared, you get 2 plus 3 factors of x. And then if you look at how many factors of x that x minus 3 to the 4th can contribute, it can contribute 4. Right, because if you multiply that all out, you're going to get an x to the 4th. If you multiply that x to the 4th times x cubed times x squared that you got from the other ones, you get 2 plus 3 plus 4. You get 9 factors of x. So your degree of your polynomial is going to be 9. That means your highest power of x and your leading term is going to be 9. You're going to get x to the 9. Which means that your end behavior, just the end behavior, not maybe the graph itself, your end behavior is going to behave just like y equals 3x to the 9. Which means, as x goes to infinity, f of x is going to go to infinity. X to the 9th is going to infinity. 3 times that is not going to make it any less infinity. And as x goes to negative infinity, x to the 9th is going to go to negative infinity. Again, multiplying it by 3 is not going to change its sign. So that's going to go to, f of x is going to go to negative infinity on the left. And if we want to find the roots, that's not hard at all. We just set x minus 1 equal to 0, x minus 2 equal to 0, x minus 3 equal to 0. And then we end up with x equals 1, 2, 3 as our x-intercepts. All right, so let's see what the graph is going to look like. Well, there are our roots. There are our x-intercepts at x equals 1, 2, and 3. Let's go ahead and put in our end behavior to our leftmost root, that's 1, and to the left, to our rightmost root, that's 3, and to the right. So to the right, it's going to go to infinity. To the left, it's going to go to negative infinity. And now let's look at that first root, that's x minus 1 squared. Since that's an even power of x minus 1, that means it's going to skim the graph. So it's going to go something like that, right? It's going to come up, touch the graph at x equals 1, and then go right back down again. Now if we look at x minus 2 cubed, that one at x equals 2 is going to look like x cubed, which means it's going to cut through the graph like that. And then x minus 3 to the 4th, that's going to come back down at x equals 3 and just skim the graph like that. And there's what our graph looks like. All right, so now you can try some of these techniques on some of the activities. The name of the file that you're looking for that's included with this video is called Graphing Polynomials from Repeated Roots.